Welcome to day 21 of the 2023 Advent of Code. So today is, unsurprisingly at this point, another grid problem. So we have a garden plot where the elf starts at point S, and then the pound signs are rocks and the dots are garden plots. And so we start from the starting position and we want to walk around. We can take a step in one of the four cardinal directions, but only onto other garden plots. And so one step lets us reach these two positions. 2 steps lets us reach these 3 new positions. In addition, we can return back to our original position. And after 3 steps, we get all of these possibilities. After a total of 6 steps, all of these marked as O are available. And so in this example, we would get 16 garden plots, but the elf needs to take 64 steps. And the map that we've been given as the real input is a lot larger than the example. Given this, how many garden plots can be reached in exactly 64 steps? So first let's grab the grid. And now we want to find the starting position. So we can say the starting row and column is the next RC for each row index R and for each column index C if the character is equal to S. And so this will find us the starting position. In our sample grid it is at index 55. In our real input it is at index 6565. Now we need to make one important observation, which is that if we reach a position with an even number of steps remaining, we can end up on that position because we can just keep alternating back and forth between that position and another position. And therefore we never need to revisit the same space twice. If we get to it, if it's on an odd number of steps, that can never change. And if it's on an even number of steps, we can always return to a S step with 0 steps remaining. And so let's do a standard breadth first fill. So we're going to begin with an answer set of nothing and a scene set of just the original starting position, and the queue will initially contain the starting position as well. Then while the queue is not empty, we also need to give it the number of steps remaining. So let's give it 16 for now so we can test. 6 so we can test with this input here. Then RC and the number of steps remaining is equal to q.pop left. And now if the number of steps remaining is even, like we said above, that means that we can add it to our answer set. And also if the number of steps remaining is 0, then we can't take any more steps, so we skip the remaining of the breadth first fill processing. Now if for each next row and column position, so we'll feed it the 4 cardinal directions. We need a couple of checks. So first it needs to still be on the grid. So if nr is less than 0 or greater than the number of rows, or the column is less than 0 or greater than the number of columns, or it's in a wall, a rock, or it's already been seen, then we skip it. Otherwise, we add it to the scene set, and then we also add it to the queue. So we append nr and c, and we decrease the number of remaining steps by 1. And now we can just print the number of positions that we added to the answer set, which is all spaces that we could reach with an even number of steps remaining. And so that gives us 16, which we expected. And now we can just adjust this up to 64. And that gives us the answer for part 1. For part 2, the number of steps we need to take is actually 26,501,365. And of course, to go along with that, the grid repeats infinitely in every direction. And so this is what our grid would now look like. So for the purposes of this problem, we once again need to inspect the input a bit. Fortunately, today's assumption isn't too egregious, but it still requires an assumption. So I've zoomed it out so we can take a look at the entire grid. And we see this is our starting position. The entire row is completely empty. And additionally, the entire column is also completely empty. Also, all of the edges are completely empty as well. The first and last column and row are each completely empty. The second part is actually true for the test input as well. However, it is not true that the row and column containing the starting position are empty. So we can no longer really use our testing input. The reason this assumption is important is because of how we're going to approach this problem. So let's say this is one instance of the grid, and let's say we're starting here. Another important assumption is that we're starting in the middle of the grid. So now when we go out a bunch of steps, we'll eventually arrive somewhere else. If this entire horizontal section is empty, and this entire vertical section is also empty, what that means is that we are definitely able to reach the furthest point possible by just walking a straight line, and so we don't need to pathfind all the way there, we can just go straight there. This also means that for any of the repeated grids in between, if we want to get to a certain position, we just need to know how far it is from that position to the closest point within that grid, because this entire segment is totally clear, and so the number of steps there is just a simple difference. So the way we're going to approach this problem is by subdividing the set of points that we can reach. So first, let's wrap this in a function. So we're going to make a function called fill, which will take up an initial starting row and column and the number of steps. And at the end, we can return the number of answer points. And so the initial state is this, and so this still works for part 1. We can say print fill of SR, SC, and 64. And so that will still work for part 1. So here are the segments that we're going to need to have. So we're going to have a bunch of grids that will fit strictly within basically the whole grid will be accessible. So if we imagine that this is our infinitely repeating grids, we'll have a bunch of grids on the boundary that are only partially reached. And so these grids with the white borders are going to be totally reachable. And so basically what we're implying is that we can reach beyond the halfway point such that when we draw the diagonal of points that we could reach, this white part is completely contained within. And so we're going to need 2 sets of coordinates for this. So another assumption that I'm going to make here is that the grid is of odd width. You can get away with not making many of these assumptions. The main reason I'm making all of these assumptions is simply to make this problem just a bit easier, because there's already enough to think about without generalizing further. So if we assume that it's odd, the width is odd, what that means is that every other grid is different. Because if the width of the grid is odd, and the number of steps that we have to take is also odd, that means that we cannot end up on the starting position again, because we can't take an odd number of steps and return to the same point. But we can reach the copy of the starting position in a different adjacent grid, because the number of steps here is odd. We also then wouldn't be able to reach this position here, because after taking another odd number of steps, we would have an even number of steps in total. So the first thing we're going to do is figure out how many grids are within this intersection. To do that, we're going to take the number of steps that we need to take, and then we're going to divide it by the grid's size. We're also going to assume that the grid is square to make things easier once again. So let's add a couple of these assertions. So first we're asserting that it's square. So let's call size the length of the grid. Now we're also asserting that we're starting in the middle of the grid. So far so good. Now we're also going to assume that the step count, let me grab that from the input here, the step count of 26501.365, we can call that steps. We're going to assert that that is a multiple of size plus size over 2. So what I mean by that is after taking this many number of steps, we're going to have a whole number of grids plus half of the size of the grid. In other words, if we go to the furthest point, we will reach the exact end point, the exact edge of one of our repeated grids. And so we're going to assert that the number of steps modulo the size is equal to the size over 2. This no longer works for the test data, so from this point forward, we're basically just going to ignore it. The reason I'm pretty confident in making this assumption is because if we print out the number of steps divided by the size, we get 2023 with 2 zeros after it. Given that the year is 2023, I feel like that can't be a coincidence. I also saw other people mention that they had this as the case for their answer as well. And usually only the real input file changes between users. Stuff like this that's coded into the problem are usually going to be the same. It's also likely not a coincidence that 64 is just few enough steps that we don't reach the edge of the grid. And so this, given that our width is 131, is also probably the same between all users. So the input size is probably the same, and this number is the same as well for everyone. And so now we're going to first determine the number of basically the grid width of the number of steps. For this example here, it's going to be 2. And the reason I picked 2 and not 3 is because this grid doesn't really count. It's kind of the midpoint. And so it's easier to operate with these two. And so we're going to take the number of steps, floor divided by the size, and then we're going to subtract 1. Because given our previous assertions, we're going to arrive at the endpoint of one of our grids, which means that our diagonal will roughly look like this. And so we're not going to be able to reach this grid fully. And so in this example, steps divided by size would be just under 3.5. So when we floor it, we get 3, which includes the starting grid, so we'll subtract 1. So the grid, we can call grid width equals the floor division of the size over, the steps over the size minus 1. Now we need to calculate the number of even and odd grids separately. So I'm going to color the even grids red first. The odd grids red first. So these are called odd grids because the number of steps that it takes us to get into them is, the number of steps that we start with is odd. So in the center grid, we start with 2651365. In the next grid that's colored red, we also begin with some odd number of steps. And so I won't go into too much detail about how to compute this, but basically if you take the grid width and then you round it down to the nearest multiple of 2, if you then add 1 and square it, you'll get the number of grids here. So in this case, we have 2 grids. If we round it down to the nearest multiple of 2, we get 2, and then we add 1, so we get a 3 by 3. And we can see here that this forms a diagonal 3 by 3. It isn't too difficult to prove why this is the case. So the number of odd grids is going to equal grid width rounded down to the nearest 2, which we can do by floor dividing it by 2 and then multiplying by 2 again. And then we can add 1 and square it. The number of even grids, on the other hand, is going to be if we round it up to the nearest multiple of 2, and then just square it directly. So in this case, there are only 4, which is a 2 by 2. If we were to add another layer of grids on the outside, we would get a grid width of 3, which means that if we round it up to the nearest multiple of 2, we get 4. And so we would indeed have a 4 by 4 of even grids. And so we can say that even equals the grid width rounded up, so plus 1 floor divided by 2 times 2, and then we don't add 1 this time and just square it directly. So in our real data, the grid width is 2022.99, Again, remember that the center grid does not count in the grid width. And then the number of odd grids and the number of even grids is some pretty massive number here. Now to process this, we're going to need to know how many points within each grid are reached. So technically we are making a bit of an assumption by assuming that we're not going to have to make any like twists and turns that cause us to not be able to reach some point like here, for example. But given that the grid is pretty sparse overall, like if we zoom out again, it's overall fairly sparse. It's also quite interesting to observe that there are just really large diagonals that are empty here. I don't think that's relevant though. Given that the grid is relatively sparse, we can assume that we won't have to make any twists and turns that cause us to waste too much time to reach any of the corner points. So in order to determine the number of points that can be reached on odd grids, we're going to say that the number of odd points is if we fill starting from the start position with a starting size of size times 2 plus 1. This just needs to be a sufficiently large odd number such that we obtain all points within the grid. It doesn't matter exactly what it is, as long as it's large enough. And we know that size times 2 plus 1 is large enough because that's large enough to get from one side of the grid all the way to the opposite corner. And since we're starting in the middle, we don't even need that much. Likewise, the number of even points is just going to be size times 2 on its own. So if we printed the number of odd and even points, this is the number of points that can be reached on each of the odd grids. And this is the number of points that can be reached on each of the even grids. And so let's start computing our final answer. So the final answer will begin with the number of odd grids times the number of points per grid that can be reached, plus the number of even grids times the number of points per even grid that can be reached. So that gives us this number here. But of course we're not done yet. Now let's handle the literal corner cases. So for each of these top, right, bottom, and left grids, we're going to have something that looks roughly like this on each side. Essentially, it's once we arrive here, all of the remaining points that we can get to, because we can cross the grid with the last remaining steps, but we can't reach the corners because of how the Manhattan distance, which is just the distance only making cardinal direction steps, because of how that works. And so the top corner, which we can label with corner T, is going to be the number of points we can reach if we fill with SR. Sorry, the starting row is going to be the grid size minus 1 because it's the bottom row. And the starting column is still SC. And the number of steps remaining at this point is going to be size minus 1. Because remember that we made the assertion that the number of steps in total is enough to get us just to the last edge of the grid. And so starting from the bottom edge, because we need to start inside the grid for the fill, the number of steps remaining to get up there is the grid size minus 1 because of offsets. Likewise, the right corner is going to be if we start at the starting row and column 0. The bottom corner is if we fill starting from row 0 and the starting column. And the left corner is if we start filling from the starting row and the rightmost column. And so we can add all of these on. So that gives us a bit closer to our answer. And now we have 2 more sets to deal with. So this is roughly what the grid looks like at the very top. And so we have 2 cases. We have this small segment here and this large segment here. Let's compute this small segment first. So at this point, we have size minus 1 steps remaining. To get to this point here in the corner, it's going to take us size floor divided by 2 plus 1 steps. And so what we have is size minus 1 minus the size floor divided by 2 plus 1. And so size minus floor divide of size over 2 is just equal to the ceiling divide of size over 2. And since size is odd, which we don't even really need to assume because it's a given in the problem, that's equal to floor divide of size over 2 plus 1. And so in other words, if we combine these two terms, we get this. And then because we're subtracting 1 here and then once again here, this turns into minus 1. And so we get size over 2 minus 1. So we'll call this fittingly the small segment, and there will be a top right variant, a top left variant, a bottom right variant, and a bottom left variant. So we're going to call it small top right. In this case, we start from the bottommost row and the leftmost column. So size minus 1, 0. And again, the number of steps is size over 2 minus 1. The bottom right segment, we start from the top row and the top column. The top left variant, which I actually said first in the order, but it doesn't matter. We start from the bottom row again, and also the right column. And the bottom left version, we start in the top row and the right column. This time we're not just adding one of these. In this example here, with a grid width of 2, the number of times we observe this segment, which I'll color in green, is for each quadrant 3 times. So it's the grid width plus 1. So we're going to say grid width plus 1 times the sum of all of the small segments. And so that gets us a bit closer. And the final section we have are these large segments. So to get to the large segment, we first consider this baseline point. So to get here, we have size minus 1 point remaining. To get here, we therefore have 2s minus 1 points remaining. And so we can either consider going from this direction or this direction. We basically have the same computation as we did here. And so this is just going to be 3s over 2 floor divide minus 1. We're basically just taking this and adding a whole s to it, which is intuitive if we consider going from the top point down. Or we're starting from 2s minus 1 and subtracting floor div s over 2 plus 1, which makes sense if we're going from this direction. It's the same thing. And so we'll call it large tr is equal to, and we're filling from the same corner, so we can just copy all of this over, rename these to large, and then just change this to be size times 3 floor divide by 2 minus 1. The number of times these occur is not going to be grid width plus 1. I'll label them green again because I'm running out of default colors. It's just going to be the grid width. And so we'll just say grid width times the sum of all of the large ones. And that will give us our answer for part 2. So I'm certain that this problem could be done a bit more generally and we could skip some of the assumptions. For example, you could technically get around the assumptions that we start in the center of the grid. You could also get around the assumption that we are taken exactly to the edge of a grid. All of those assumptions were just to simplify our logic a bit, because most of these can just be assumed directly, like this one for example. The grid width is pretty much guaranteed to be constant between users. This value is not variable. And also, again, the 2023 and then with 2 zeros at the end is a bit too good of a coincidence to not be an Easter egg inserted by the creator of this problem. And so you could generalize this a bit more, but I feel that these assumptions are all fairly reasonable to make and definitely help with making the logic a lot simpler in the end. In any case, thank you for watching, and I hope you enjoyed.